Okay, we might get started. Hopefully we've got Olivia online with us still. Olivia is our second speaker for this evening. She is a PhD student with the Institute for Sustainability on the Global PhD program in Sustainable and Circular Technologies between the University of Bath and Monash University. Olivia has a master's in material science and engineering from the University of Manchester. Her PhD research is in materials engineering and chemistry titled Peptide Polymer Fibres, Novel Structures, Synthesis and Applications. She focuses on biomimicry for textiles, improving the sustainability of textile production and finding new functional textiles for medicinal applications. Again, I am fortunate enough to have the opportunity to collaborate with Olivia both professionally and as a friend. So let's welcome Olivia to the Zoom stage. I will stop sharing.
Okay, so yeah, I am going to talk similar kind of maybe a little bit of overlap with what Terry talked about. I'm specifically talking about mimicking coloration in nature and one specific mechanism that scientists are trying to mimic. So this presentation, I'm going to talk about structural color and its role in nature. And I'm going to talk about the mechanism of how that structural color is produced and how then the scientists are mimicking the structural color. I'm just going to get my laser pointer on before I forget. So actually, I learned about the structural color in the University of Manchester, which is the home to Henry Ford that Terry talks about. So it is the home to the production line, to the mass production manufacturing process. However, I chose to go to the University of Manchester because it was the birth of the mass-produced textiles production line as well. And it is a great home to textiles research. But in this generation has become a great home for sustainable research in materials as well. So I did my bachelor's and integrated master's in materials science and engineering. And then I did in my master's year, I joined AHU in the biofilm group, which is primarily focused on trying to achieve the more self-assembly routes with biomimicry. And I think their work is really fascinating. They have a great webpage if you want to have a look. And the work that Terry mentioned about the comparison between our dominated, I wrote it down, I thought it was a really good line, dominated by thermodynamic control and energy consuming assembly, whereas nature has this, for example, self-assembly processes, etc. So the biofilm group focuses on that, and I learned all about the structural color and the process, the mimicking process that I learned from this group. I'm not going to share the work I did with them because it wasn't published. I did it during COVID. We had really limited time, and then I had to, laboratory access time, and then I had to go on to do my PhD. So I don't want to share something. And I'm now doing my PhD I'm currently in Australia at Monash University, but my home institute is the University of Bath, also in the UK, with my supervisors Hannah Leese and Andrea Robinson. And I've started collaboration with Louis Karatzis at CSIRO for textile, for fibre production. And my PhD does focus a lot on biomimicry, improving the sustainability of textiles using biomimicry methods. So I'm a big fan of this topic. So yes, the structural color that Terry really well introduced and talked about a wide range of mechanisms. I'm going to focus solely on one mechanism that produces the iridescence. Structural color has come about in nature with the evolution over time for purposes in mating. So they would be bright colors, but it would also be purposeful for camouflage. So due to the mechanism I'll explain later, they would be seen really brightly to their own species for mating purposes, but quite a dull color to their prey, for example, to not be eaten. In the plants, so I've got a berry here that has an iridescent color as well, and it would look very bright to the animal that would eat it to then spread its seeds around the area, and it would further grow in other places. And structural color in other mechanisms as well has been thought about to become as UV protection and help photosynthesis as well and pollination. And I would like to point out that there is I'm not here to advertise, but there is a 2-episode series by David Attenborough which focuses on this, and I thought it was really great to watch. And I include this because I remember it talked quite a bit about pollination and how that works because of structural color. So that was really interesting. So the specific structural color I will talk about is made from, it comes from the cellulose microfibrils and the chitin in plants and chitin microfibrils in animals. And the chitin microfibrils schematic that I've used is from Ahu's group that I mentioned before. So these microfibrils will be stacked in a certain way to refract light, and then we therefore see the color. So here you can see there is a helicoidal twist due to the stacking of the chitin microfibrils. And due to that twist, you see the iridescent appearance as well. So just to kind of try to explain this briefly, I'm going to use the Bragg's diffraction law if you've heard of it. However, if you're going to go deeper into it, it is the Bragg-Snell law that it uses. But I'm going to try and just keep it quite brief here. The Bragg's diffraction law is to do with the refraction of the waves from light source. So the incident light will come in and at a specific angle will refract out at the same angle, and this determines the wavelength of light that we see. So that wavelength of light that we see is affected by the diffraction grating. So we have some atoms here that are kind of symbolizing diffraction gratings, and the distance between these atoms is the distance between the diffraction gratings. And so the wavelength of light that we see come out of the refraction can be changed by the change of the distance between the diffraction gratings. So if you keep that in mind, and here I have kind of shown the helicoidal twist that you saw on the previous page. I've shown each plane of the nanocrystals stacked, and as they twist around, you also get a change in the angle as well, which is what brings about the Bragg-Snell law. But if we think about with the Bragg's diffraction law, you have here at the top, so it looks here like a flat plane, and at the bottom a plane parallel to that. So that is a 180 degrees twist of the nanocrystals, the microfibrils that are stacked, and that is half a pitch. So if you see that as a diffraction grating that you see in the Bragg's diffraction law, you can put it into the Bragg's diffraction law as one pitch can determine the wavelength of light that we see. And in addition to that, due to the change in angle, and so the helicoidal twist that we get, you get circularly polarized light. And so we can view this under something called a polarized optical microscope. And I've shown here the jewel beetle. You have here under the left-hand circularly polarized light, it is very bright, and under the right-hand circularly polarized light, it's very dull. And so this is what I mentioned before when I said the animal's own species will see in one polarized light to see the other species brightly for mating purposes, and in the other circularly polarized light direction, the prey would view this and it would appear dull. So it's due to an evolution adaptation as well for survival purposes. And maybe some of you have heard of a white peacock. And I think this is a really cool example of this. So if you see a white peacock, it has exactly the same structure to reflect the light in exactly the same way. However, it doesn't have melanin. So melanin is natural in the animals and the plants that creates this black background and allows us to see the bright color that's reflected. And I've included a great schematic here, actually from a biomimicry paper for textiles. So the melanin black background will absorb the stray light that is scattered to see the bright color. So you see here without the black background, you get this MIE scattering and it all appears white, and it's a low saturation of the refracted light. So this paper was really cool. It was something I looked at during my master's, where they coated silicon nanoparticles with polydopamine. So this is something that scientists also use for mimicking melanin from nature, polydopamine. And then they found that the melanin-like nanospheres were self-assembled by gravity deposition. And so then formed this coloration surface on the textile, on the fabric, which I thought was a really great paper. And so I'm going to now talk about how scientists mimic this structural color in nature. So the one that I have looked at is with cellulose nanocrystals, and the earliest paper I could find on it was in 1998. So it's quite well known. And so what I did was I got like filter paper and did a hydrolysis method, and then you get these cellulose nanocrystal rods suspended in water, and it's an isotropic phase, and due to charges around the nanorods, you get like these repulsive forces, which is something called the Onsager theory, if anybody is interested in that. And it allows them to maintain this isotropic phase in the water suspension. So you see underneath here in this figure that after the hydrolysis method, you get these charged groups on the surface of the cellulose nanocrystal rods, and you get different ones depending on what hydrolysis method you use. So then once you've got your suspension and you do room temperature evaporation overnight, it's this part is very low energy, and then the cellulose nanocrystal rods will start to self-assemble within the suspension. So as the nanorods become more concentrated, the concentration of the nanorods increases in the water, they begin to self-assemble. And here I've shown like tactoids, which is what they call them. They're like pockets of ordered formation, and they continue to grow. So doing this just very simply and in very low controlled conditions, I get kind of just like a film of, you do get this kind of colored, ordered, structured domains of color, so little pockets of different color, because the self-assembly has such a lack of control. And this is something Terry points out as well, how well nature does it. Nature gets these super pristine coloration, whereas just doing this simply like this, we get just kind of a quite a mix of colors and capillary forces. You get the coffee ring effect, etc. So this was one of the first films I tried to make just by using this well-known process. And so eventually, yeah, you get this solid film of color, and it's irreversible. However, to view this color, I had to put it on a black background. If I held it up off the surface of a black background, because I evaporated, I did this evaporation process on a glass slide. So if I just held it up, you couldn't really see the color. So it also gives those properties for kind of the iridescent films as well, because it does have the, I forgot the name of the method, but the use, but it's to stop, it's to kind of put a mark on, say like on banknotes, etc. You have that that mark, that iridescent mark on the banknotes. So it gives that effect. And you see here how the nanorods have their charges on the surface, and then they have something, so that's their electric layer, and then they have their double electric layer just around. And so this is what determines the separation of the cellulose nanocrystal rods in the structure after the self-assembly has formed. So you get this helicoidal twist, the same as what I explained before. And then you, as I will just remind, reiterate what I said, you get the half a pitch here with the 180 degrees twist, and that kind of acts as a diffraction grating in Bragg's diffraction law. And so then if you think about this pitch and the diffraction grating, you can actually shift the color. So if you reduce the diffraction grating, so you reduce the pitch, and you reduce the pitch by reducing the separation between the cellulose nanocrystal rods, you reduce the wavelength of the light that we see, so we would see a more blue shade. And this is a very sensitive process. But addition of electrolytes, for example, is something that be done to reduce the separation distance, and changes of pH will also change the pitch as well. And there's a number of different ways that it can be done as well. And then again, so increasing the double electric layer, increasing the separation between the planes of the cellulose nanocrystal rods will increase the pitch, and therefore increase the wavelength of the light that we see. So we'll shift towards a more red color. And it can be done by sonication, and again, change in pH and fillers, etc. But as I mentioned before, it is such a highly sensitive process. It's a long way off of becoming something to have as colored films of a specific color now at the moment. We can't yet do it as well as nature. And so here's a paper that I recently found where they did get some really good color shifts, and they were using this PEG glycerol filler solution. So yes, this is a green webinar, and PEG wouldn't be the first option, but I think if you can prove a concept and then you can try and adapt to a more sustainable material, I think that's a good approach as well. So yeah, I basically replicated what these guys did in my laboratory recently at CSIRO. So I got the cellulose nanocrystal suspension, and they added glucose to homogenize the suspension, and then they added this PEG and glycerol filler solution at different weight percentages. And so at a low weight percent, I got blue, and they got blue. 20% was green, and 38% was red. And so you can see you're increasing the pitch. So you're increasing the distance between the cellulose nanocrystal rods in this helicoidal twist, and therefore increasing the wavelength of color that we see. And again, I have to put this on a black background. I did the self-assembly method on just some Petri dishes, but changing the surface that it self-assembles on does also change the end result as well. So it has to be adapted for its use. The main reason I've continued to look at this is because the textiles industry, I'm sure many of you are well aware that the dyes that are used cause insane amount of pollution around the factories, especially in China and India, the rivers, and other countries as well. And then also when they're in use and they're being washed, what comes off in the washing and goes into the ocean. Some really interesting thing that I found out during my literature review for my PhD was that, so you have polyester microfiber plastics. I'm sure many of you are well aware of those from your clothes that come off in the washing machine. However, the bigger percentage that we have is cellulose microfiber plastics, but they're actually not degrading because they're coated by these dyes. So while you might be thinking, oh yeah, I'm doing great, I've got like a bio-based textile clothing, they're actually not any better because they're coated by dyes, by toxic finishes. So by looking at trying to improve the sustainability of the coloration that we see in textiles, I think would be amazing, because it is currently second to, the textile industry is currently second to pollution in, second to the oil industry in global pollution. So thank you for listening, and I look forward to any questions in the breakout room.